Hey everybody, we're going to be talking about ion concentrations and yet another Mr. Z teaches chemistry during the apocalypse video. Here we go. So to understand ion concentrations, I'm just going to give you guys a little bit of a picture. Okay, there's Mr. Z. Hi. All right, so, well, Mr. Z is quite tall. That doesn't make sense. All right, so here is Mr. Z's girlfriend in high school. Together, they are a couple. But once she figured out that Mr. Z was kind of a loser, they broke up. And they separated into one free Mr. Z, he's crying, and one free girlfriend. So they were separating into different entities. Now, okay, so this is where this system breaks down because we shouldn't get into more than one people in a relationship. But let's say you had 3 blocks, and one of those blocks is red. 2 of those blocks are green. When that system separates, if you break all the blocks up, you get 2 free green blocks and 1 free red block. And we're going to be using, so this is there's 1 of these, 2 of these, and 1 of those. Okay? So that's mole ratio when you separate compounds into ions. And we're going to be looking at the math of that today. It's actually a big deal. Because you remember how we could use mole ratio to figure out, for example, moles in a gas system or volume in a gas system? We can use the mole ratio to figure out concentration in a solution system. Okay. Oh, that's the one from a second ago. Okay. Ion concentration in solution. Okay. So what are the ion concentrations of a 0.5 mole liter solution of aluminum nitrate? Okay. Now, here is something, breaking down all of the math that we've done so far. This is not parts per million. This is not percentage. This is not dilution. This, if it's asking for ion concentrations, this is another step to the puzzle. And we need to write out the dissociation of aluminum nitrate. So you start with aluminum nitrate. Aluminum is 3+, right? Some people were having trouble with their ion charges on the entity assignment last week. And we would need 3 nitrates for every aluminum. Now, when this system breaks up, we are left with 1 aluminum and how many nitrates? That's right, children, 3 nitrates. So that is a dissociation. Now, it would be a very easy question if this was instead sodium chloride. But based on this, take a look at this. It's really cool. We have 0.5 moles per liter. Now, you remember that times by where you're going, divide by where you've been? Where have you come from? Where'd you go? Where have you come from? Avogadro, right? There's a joke we made in IB. So if we wanted to figure out the concentration of the aluminum ion, let's just change this to aqueous. Okay, spoiler alert, everything has to be aqueous for this to work. It was supposed to be, that's typo. But so these compounds are the exact same ratio mole-wise, 1 to 1. So the concentration of the aluminum ion doesn't change. There's the same amount of stuff per liter, because it's a 1-to-1 ratio. Now, what do you think happens when we go to the nitrate ion? Yeah, this is a little trickier. What's the ratio? Well, we have 3 times the amount, right? There's a 1 here. So we would multiply the concentration by 3. 1.50 moles per liter. Now, if you look, from here to here, we have 3 times the amount of nitrate to aluminum. and the concentration is tripled between the two. So the math checks out. So when finding ion concentrations, you use mole ratio to solve it. Okay, we're going to come back to a little tougher problem, but we're going to do one more example together, and then we're going to move on. Okay, what if we had, let's say we had, I don't know, what's a good example here? Something with a really, really big charge. Let's like technetium chloride. Whoa, technetium is 7 plus. Okay. Let's say this was 0.1 moles per liter. What are the ion concentrations? So we have to break this up. Technetium breaks up into a 7 plus ion. How many chlorides are there? 7 chlorides. Perfect. These two are in the exact same ratio, 1 to 1. So the concentration of the technetium ion and the technetium chloride is exactly the same, 0.1 moles per liter. But when we go from technetium to the chloride, times by where you're going, 7, divide by where you've been, 1. So the 7 is right there. That goes on top. The 1 is below. So our math is 0.1 moles per liter times 7 over 1. That's 0.7 moles per liter. Most of the time, these are going to be very simple problems because you're either going from the ion back to the original compound or from the compound to the ion. And usually, this is a 1, so you don't have to worry about having weird fractions. But that's the idea. You start with a block that has many ions all together as one group, and then something comes along, causes a little bit of heartbreak, and now you have 2 charged particles that are the same. Now, this is where this thing kind of gets disappointing. Maybe Mr. Z was trying to hit on 2 girls at the same time, and of course that would fail horribly. So now Mr. Z is out at a 1 to 2 ratio because he's a terrible, terrible person with trying to talk to anybody. Okay, let's try a little bit tougher problem. Oh, that's the one from earlier. Okay, so I think we're getting this mole ratio. We've already practiced mole ratio. Now we're going to pump up the jam with a tougher one. This says, what are the ion concentrations of a 4.5 gram sodium carbonate dissolved in 500 milliliters? Now, ions and concentration is moles per liter. So because we want ion concentration, we need to write out the dissociation reaction. However, we're not given concentration, so we've got 2 steps to this. One is a dissociation, and the other is unit analysis. So this is 2 problems in one. Okay, so let's write out the dissociation. Sodium carbonate. Sodium is 1 plus. Carbonate is 2 negative. 2 sodiums to 1 carbonate. When it breaks apart, we will have 1 free sodium ion and 1 free carbonate ion. Now, reading this problem, we've got 4.50 grams of sodium carbonate. We have 0.5 liters, right? I just turned the milliliters into liters. And because we have mass, what goes with molar mass? You're right, children. I gave that away. What goes with mass? Molar mass. 2299 times 2 plus 1201 plus 16 times 3. Okay, I get 105.99. 105.99 grams per mole. Now, I need all of these variables. This is just like one of the questions we did last week. We're just going to add one extra step to this. We need to solve the moles per liter of this before we can move on. So getting moles on top, we'll use the molar mass, but we'll flip it. Mole over 105.99 grams. Grams go on top. cancel out grams, and we need volume on the bottom. So I'm going to put the liter on the bottom. Grams cancel. Oh, pen down. And now we've got mole per liter. So when I multiply this out, 4.5 divided by 105.99 times 0.5, I get fairly small concentration, 0.0849 moles per liter. Now, that's the concentration of the sodium carbonate. That's not the concentration of the ions. But if we look, which one of these compounds is a 1-to-1 ratio with each other? If you said the sodium carbonate, because it's balanced for 1, and the carbonate, which is balanced for 1, then the concentration of things that are the same is the same. 0.0849 moles per liter. Times by where you're going, divide by where you've been. So we're going to figure out what sodium is. Times by where you're going, 2. Divide by where you've been, 1. So we have twice the amount. So when I multiply that by 2, I get to 3 sig figs, 0.170 moles per liter. Now, 9 times out of 10, that's the answer. Now we've got everything in ion concentration. 9 times out of 10, the problem's going to be like this, where you have to find the ratio. You don't have to do any of the tough math because it gives you the concentration. Occasionally, you're going to have some ring dingers, which give you the mass, and you have to first find the concentration, and then the ion concentration. And I know some of you are like this, but that's chemistry. So turn that frown upside down. That's right. Now you're upside down. Okay. All right, that's this video.